Well, today we'll be talking about a high altitude balloon model that we made for the ASEN 2002 Balloon Lab. I am Alessandro.
I'm Travis.
I'm Ahmed.
And I'm Joe.
And in this presentation, we're going to go through the project parameters, design choices, and models that we made in order to make the perfect model for this lab. But we'll be going over governing relationships and design elements, as well as all the analysis we did to bring you the perfect model.
Yeah! Woo! All right, so as you guys well know, as far as project definition and interpretation goes, we have to design a high altitude balloon that meets certain specifications and requirements. So we will be choosing the material we use, the factor of safety, as well as the size, including volume and thickness and radius. We're going to be utilizing thermodynamic principles to create a realistic and working design. We're going to analyze intensive and extensive properties, as well as use MATLAB to do our calculations and our plots. So for our design requirements, we decided to have an experimental payload, meaning that we're not going to have any humans on the balloon itself when it's in the air. So that payload is going to be 500 kilograms. We also have to stay at an altitude of 25 kilometers, give or take a kilometer. And then we need to stay up there for 24 full hours. For the factor of safety, we chose to have a factor of safety of 1.5. We did this based on relative missions with similar payloads just that have been done in the past. So some of the key assumptions for this project, we are assuming that we have a spherical shaped balloon. We are assuming that the balloon radius is much greater than the thickness, making the thickness negligible. We're going to be ignoring transients of ascent, meaning that we're going to be just appearing at our 25 kilometer altitude. We're going to be ignoring stresses caused from the payload, as well as the payload mass includes everything that's needed to attach the payload to the balloon. So for our design choices, we ended up choosing, for our material, we had Borealis FG5224 linear low density polyethylene, also known as LLDPE. So that is our material we chose. It has yield strength of 12 megapascals, a density of 0.922 grams per cubic centimeter. It is available in small thicknesses, and we did this based on flight heritage as well, meaning that it has been used in the past. It's well known in the aerospace industry, so we know that it's a reliable material to use. For our looking glass, we have chosen helium, and based on our calculations, we ended up having a radius of 15.87, which is a little bit greater than our initial radius, but we will get to that later on in the presentation. So we got this thickness based on the functions of fields, factor of safety, yield strength, radius, and pressure, as well as utilizing the neutral buoyancy equations. So with that radius, we ended up getting a volume of 1.67 times 10 to the 4th meters cubed, as well as a thickness of 9.92 microns. And again, we have a spherical balloon shape. Our radius is much greater than our thickness, as we see, and the balloon is also non-expanding. So as far as models go, we began the lab actually doing a scale model using a paperclip, a normal sized balloon that did have a mylar skin, which is another polyethylene, and we filled it with a helium gas, and we had a certain payload on it. So with that scale model, we were able to use the ideal gas laws and force balance equations to perform calculations to find the mass of the helium itself. We also worked to achieve the neutral buoyancy, and in the full scale working model to maintain the neutral buoyancy. Also in the scale model, we had a heater, and we did this to practice the radiation, to simulate the radiation that would cause the gas to expand in our real model. And we were able to find the thermodynamic equilibrium at the minimum and maximum altitudes based on that model.
And just as Travis mentioned, we used different equations to come up with this model. One of the equations we used is the ideal gas equation, and part of that is that the pressure of helium equals the pressure of the air plus the gauge pressure, and the density of helium equals the pressure of the air over the gas constant of helium times temperature. And then we use the factor of safety equation. This helped us derive relationships between factor of safety, thickness, and the pressure found from the gauge. Using these equations, we could help develop a MATLAB script furthering these next equations, the force balance equations. Since we wanted to achieve neutral buoyancy, we had to make sure that these equations equaled each other, or if you subtract them, that they added up to 0. We use these equations to figure out what masses we wanted to account for, such as the mass of the payload, the mass of the film, and the mass of the helium. And of course, we have the volume calculation of our sphere, and then we also have the volume of the film based on the thickness that we used, relating back to the factor of safety. Onward, in order to develop our design, we had a couple steps. So this included comparing shell materials and lifting gases for some initial research, then moving on to choose a factor of safety and solving for the radius and thickness using that factor of safety using a system of equations, and that allowed us to create a volume calculation for our balloon. Then we actually went backwards and checked out our factor of safety, checked out our radiuses, thicknesses, and did some analysis to choose our final material and choose our final factor of safety of 1.5. After that, we solved for some temperatures during the day and night to figure out how high our balloon will rise or how low our balloon will fall. We use these temperatures to do analysis and calculate the change in altitude. Then using that change in altitude, we calculated a ballast needed, and the ballast needed to be dropped to stay within that altitude. And then finally, we verify that with that new ballast, the balloon stays within its altitude, completing these mission requirements. As mentioned before, we compared a couple different materials, and these are just the three major ones we compared. So the highest line, the one in orange, being LLDPE, Borealis linear low density polyethylene, and that's the one with the steepest slope. And then you have the middle one, which is a rubber material, and that has a medium slope. And then we have the polyester from Mylar that has the lowest slope. And you can see that at approximately 1.5 factor safety, we have the highest volume yielded from LLDPE. And using that, you can derive that it's about 1.55 meters cubed in that volume. Onward, using the LLDPE, you can see that we did graphs of factor safety versus radius and factor safety versus thickness. And these graphs are obviously functions of volume, as these are used to calculate that volume. You can see that approximately 1.5, you get a respective radius and thickness based on these graphs. And this helped us further analyze the relationship between factor safety and radius and factor safety and thickness.
Now, as everyone knows, temperature changes throughout the day and the night. So because of that temperature change, we had to do some thermal radiation analysis. And as we saw in the scale model, when we heated up a balloon, it increased the volume of the balloon, which then increased the altitude. So to find the minimum and maximum altitude of our balloon during the day and the night, we first had to find the temperatures. And to find the day temperature, we set the thermal radiation out from the balloon equal to the thermal radiation from the sun plus the thermal radiation of the earth. And at night, we just set the thermal radiation of the balloon equal to that of the earth. And this resulted in a day temperature of 0 degrees Celsius and a night temperature of negative 93 degrees Celsius. Then we took those temperatures and plugged them into the ideal gas law and used that to find the new volume of the balloon at that altitude, or at that temperature. And finally, we took those volume to get an overall density of the system and compared that overall density to the density of air at different altitudes to find the final altitude of the balloon. So with our initial radius and thickness, the balloon would be too high during the day and too low at night by about 300 meters in both directions. And we tried changing our radius and thickness and factor of safety to try to get it to stay within our 2-kilometer range, but those changes weren't significant enough. So we had to add a ballast. And basically what that is we add an extra mass onto the balloon that we drop at night so it can stay within the altitude range. And we also had to increase the radius of the balloon so it could still carry 500 kilograms at night. We found that a ballast of 80 kilograms was the best amount to use to keep us in the range. And we chose sand as our ballast material since it's cheap and relatively safe to drop from a high altitude. Now here's a rough visualization of our altitude throughout the day cycle. And some assumptions to simplify this graph is we assume that the altitude followed a sinusoidal curve and the change in elevation due to the ballast was instantaneous. So we started the balloon at 25 kilometers right at morning, and it had 580 kilograms, which is the 500 kilogram payload plus the 80 kilogram ballast. And now here's a bigger visualization of that. And you can see it reaches a max altitude of 25,936 meters at the hottest point in the day. And then after 12 hours have passed, we drop the ballast and it rises up so it only reaches a minimum altitude of 24,078 meters.
So our preliminary analysis shows that our design is feasible, as my colleagues just proved. Whilst we may not know exactly the behavior of the balloon throughout its flight, we do know that it will follow a roughly sinusoidal curve because, of course, as we all know, the Earth is a sphere. However, if we know that some of our assumptions were not correct, like assuming that the balloon would have maintained the shape of a perfect sphere throughout the ascent, but it would not be too difficult to adjust our MATLAB code to take into account different thicknesses of the different shapes of balloons given different volumes. However, there still are some lingering uncertainties. What would the shape of the balloon be under load, and how does this affect flight? And is the production of such a large-scale balloon in the scope of this team, or even any company for that matter? So further investigation is necessary in order to gain a better understanding of the performance of the balloon. Some areas of interest include a material analysis at different pressures and temperatures, because polymers are notoriously capricious at different temperatures, as well as the factors of safety at these temperatures. We should also be conducting a test flight of our data in order to assess different altitudes and times and to better understand the atmospheric model. Because please remember that the model we are using at the moment is from 1971, and the climate of the Earth has changed considerably since then. We should also research and design different balloon shapes with accompanying thickness in order to avoid failure. Because as I said earlier, spheres are, we do not live in an ideal world, and we should not be assuming that our balloon is a sphere. We may also do a multi-megavariate analysis of all our data with the factor of safety and thickness in order to guarantee success. I've already done a little bit of research into the shape of high altitude balloons, and on the left graph you can see that the balloon takes more of a teardrop shape with a non-uniform density, having a thicker density at the top in order to account for the stress. And on the right side we see different shapes of balloons, with the lowest shape being a balloon which has a string that connects the top of it all the way down to the payload mass in order to maximize the stress and the strain caused by this. Both of these were found relatively easily, and more research will definitely yield better designs and better results. Thank you again for coming. Don't forget to smash that like and subscribe button.
Feel free to check out other references we use in order to find different material properties, so we can find those graphs that you saw earlier.